Hello everyone. So this tutorial is about the sliding window protocol. So we'll see the definition of sliding window protocol. A sliding window protocol is a feature of packet-based data transmission protocols. Sliding window protocols are used where reliable in-order delivery of packets is required, such as in the data link layer of OSI model, as well as in the transmission control protocol. So there are basically three types of sliding window protocols. The first one is a one-bit sliding window protocol, that is stop and wait. The second is a protocol using go back N, and the third is a protocol using selective repeat. So these three protocols differ among themselves in terms of efficiency, complexity, and buffer requirements. As in all sliding window protocols, each outbound frame contains a sequence number ranging from 0 up to some maximum value. The maximum value is usually 2 raised to n minus 1, so that the sequence number fits exactly in n bit field. The essence of all sliding window protocols is that at any instance of time, the sender maintains a set of sequence numbers corresponding to frames it is permitted to send. These frames are said to fall within the sending window. Similarly, the receiver also maintains a set of sequence numbers it is permitted to accept. The sender's window and the receiver's window need not have the same lower and upper limits or even have the same size. In some protocols, they are fixed in size, but in others, they can grow or shrink over the course of time as frames are sent or received. The sequence numbers within the sender's window represent frames that have been sent or can be sent but are as yet not acknowledged. Whenever a new packet arrives from the network layer, it is given the next highest sequence number, and the upper edge of the window is advanced by 1. When an acknowledgement comes in, the lower edge is advanced by 1. In this way, the window continuously maintains a list of unacknowledgement frames. Let us see an example. Initially, the upper and lower edge of the sending window is at 0, while the upper edge of receiving window is at 1 and the lower edge is at 0. After the first frame is sent, the upper edge of the sending window goes to 1, while the receiving window remains the same. After the first frame is received, the sending window remains the same, while both the upper and lower edges of the receiving window are advanced by 1. After first acknowledgement is received, the lower edge of the sending window goes to 1 and the receiving window remains same. Now we'll see the first type of the protocol, that is the one-bit sliding window protocol or the stop and wait protocol. This type of sliding window protocol is the one in which the maximum window size is 1. Such a protocol uses stop and wait since the sender transmits a frame and waits for its acknowledgement before sending the next one. Here is an example for this protocol. Assume that the computer A is trying to send its frame 0 to computer B and that B is trying to send its frame 0 to A. Suppose that A sends a frame to B, but A's timeout interval is a little too short. Consequently, A may timeout repeatedly, sending a series of identical frames, all with sequence number is equal to 0 and acknowledgement number is equal to 1. When the first valid frame arrives at computer B, it will be accepted and frame expected will be set to 0. All the subsequent frames will be rejected because B is now expecting frames with sequence number 1 and not 0. Furthermore, since all the duplicates have acknowledgement is equal to 1 and B is still waiting for an acknowledgement of 0, B will not fetch a new packet from its network layer. After every rejected duplicate comes in, B sends a frame containing sequence is equal to 0 and acknowledgement is equal to 0. Eventually, one of these arrives correctly at A, causing A to begin sending the next packet. No combination of lost frames or premature timeouts can cause the protocol to deliver duplicate packets to either network layer, to skip a packet, or to deadlock. However, a peculiar situation arises if both sides simultaneously send an initial packet. This synchronization difficulty is illustrated by the figure. In part A, the normal operation of the protocol is shown. In B, the peculiar is illustrated. If B waits for A's first frame before sending one of its own, the sequence is as shown in A, and every frame is accepted. However, if A and B simultaneously initiate communication, their first frames cross, and the data link layers then get into situation B. In A, each frame arrival brings a new packet for the network layer. There are no duplicates. In B, half of the frames contain duplicates, even though there are no transmission errors. Similar situations can occur as a result of premature timeouts, even when one side clearly starts first. In fact, if multiple premature timeouts occur, frames may be sent 3 or more times. Now, let us move to our next protocol, that is a protocol using go back N. Pipelining frames over an unreliable communication channel raises some serious issues. First, what happens if a frame in the middle of long stream is damaged or lost? Large number of succeeding frames will arrive at the receiver before the sender even finds out that something is wrong. When a damaged frame arrives at the receiver, it obviously should be discarded. But what should the receiver do with all the correct frames following it? Remember that the receiving data link layer is obligated to hand packets to the network layer in sequence. In figure, we see the effects of pipelining on error recovery. We will now examine it in some detail. One way, two basic approaches are available for dealing with errors in the presence of pipelining. One way is called as go back N. It is for the receiver simply to discard all the subsequent frames, sending no acknowledgements for the discarded frames. This strategy corresponds to a receive window size of 1. In other words, the data link layer refuses to accept any frame except the next one it must give to the network layer. If the sender's window fills up before the timer runs out, the pipeline will begin to empty. Eventually, the sender will time out and retransmit all unacknowledged frames in order, starting with the damaged or lost one. This approach can waste a lot of bandwidth if the error rate is high. In figure A, we see go back N for the case in which the receiver's window size is 1. Frames 0 and 1 are correctly received and acknowledged. Frame 2, however, is damaged or lost. The sender, unaware of this problem, continues to send frames until the timer for frame 2 expires. Then it backs up to frame 2 and starts all over with it, sending 2, 3, 4, etc. all over again. This was all about go back and protocol. Now, let us see a protocol using selective repeat. We have an example here. Suppose that we have a 3-bit sequence number so that the sender is permitted to transmit up to 7 frames before being required to wait for an acknowledgement. Initially, the sender's and receiver's windows are shown in figure A. The sender now transmits frames 0 to 6. The receiver's window allows it to accept any frame with sequence number between 0 and 6 inclusive. All 7 frames arrive correctly, so the receiver acknowledges them and advances its window to allow receipt of 0, 7, 0, 1, 2, 3, 4, or 5 as shown in figure B. All the 7 buffers are marked empty. It is at this point that disaster strikes in the form of a lightning bolt hitting the telephone pole and wiping out all the acknowledgements. The sender eventually times out and retransmits frame 0. When this frame arrives at the receiver, a check is made to see if it falls within the receiver's window or not. Unfortunately, in B, in figure B, frame 0 is within the new window, so it will be accepted. The receiver sends an acknowledgement for frame 6 since 0 to 6 has been received. The sender is happy to learn that all its transmitted frames did actually arrive correctly, so it advances its window and immediately sends frame 7, 0, 1, 2, 3, 4, and 5. Frame 7 will be accepted by the receiver and its packet will be passed directly to the network layer. Immediately thereafter, the receiving data link layer checks to see if it has a valid frame 0 already, discovers that it does, and passes the embedded packet to the network layer. So this was all about the sliding window protocols. Thank you guys for watching the video. Hope it might help you. Thank you.